Hello there, thank you for joining me. My name is David Cater. In this video, we're going to be looking at how an inductor is going to behave in DC. So, first thing we're going to do is just analyze the circuit, and we're going to notice that this is a 100 volt DC source, and it's connected to an inductor of 1 Henry, an inductance of 1 Henry, and a resistance of the circuit will equal 10 ohms. A couple of things we want to do. Let's go ahead and figure out what the current, the maximum current in that circuit is going to be. And in DC, the current is going to be dictated by the resistance. So it's going to be E over R, simple Ohm's law, 100 volts at 10 ohms, and we have 10 amps of current is going to flow at max in that circuit. Okay? Another thing we want to do when we're analyzing this circuit in DC is figure out what is the value of time it's going to take for this inductor to rise to max, because it won't happen instantly like it does with a resistor. So what we want to do is figure that out. Okay, so we have a time constant formula, and that's going to be the value of inductance over resistance, and that'll get us to the very first time constant 1. So that's a very simple calculation here. So we have 1 Henry over 10 ohms, and we have 0.1 seconds or 100 milliseconds. All right, so it takes 100 milliseconds to go from 0 to the very first time constant, and we have 5 time constants in total, so that would be TC5, and that would be 5 times the total amount of time here, so that would be 0.5 seconds. All right, so in order for it to rise to the first time constant value, it takes 0.1 seconds. In order for it to rise to a steady state, it will take approximately 5 time constants, and therefore we have 0.5 seconds. Okay, now the next thing we want to do is figure out at each time constant along the graph, what is the value of current in that system. So when we look at that, first thing we're going to do then, I guess, is we want to plot out what the current is going to look like. All right, so that is going to look like something like this. It's going to rise up to a max here, and our maximum we've calculated to be 10 amps. And it's going to rise quite quickly and then level off until we hit our 10 amps. Okay, so we have a logarithmic rise here of current. Didn't rise immediately straight up, but it did rise rather quickly and then leveled off to its steady state current of 10 amps, which we calculated with Ohm's law. Now, what's interesting is the voltage across that coil is going to be only really present when there's a counter EMF, and that counter EMF is going to be dictated by a change of current, therefore a change of flux. So what actually happens to the current is very, very interesting. So we end up with something that looks like this. We have a voltage. The voltage of the coil is going to drop, and it drops sort of the opposite way that the current rises. So once current has hit a steady state, the voltage of the coil, the voltage across the coil is going to be 0 volts, and that's assuming we have what we'd call maybe a perfect coil. There's no resistance. If the coil would have resistance, we would have some volt drop there, but in our example we're going to keep it very basic. Okay, so what we want to be able to do from this point is figure out what is the value of current at the first time constant and the value of voltage at the first time constant. So we have a couple of things that we want to know, and that is, what is the rate of rise for each time constant along this graph? And what's very interesting is that it is a very, very constant rate of rise regardless of the circuit properties. And what I mean is the shape of the graph stays the same. It's just the peaks and the length that change, but ultimately it falls into a certain percentage of rise for that first time constant. All right, so for the first time constant is 1, we get a 63.2% rise of the total. So what that would look like is 63.2% of 10 amps, so that would be 10 amps times 0.632, and we of course have 6.32 amps. So that is how much current is flowing at the first time constant, 6.32. Now, that is a rate of rise for this inductive circuit in DC. Time constant number 2, if we wanted to calculate all the way through, is going to be 86.5%. Time constant 3 is going to be 95% of the total. Time constant 4 is going to be 98.2. All right, and then time constant number 5 is going to be 99.3. And so you can see by the time we've hit this 5th time constant, we're pretty much at 100%. We're going to call this one close enough. And so the calculation will be the same. Take our 10 amps, multiply it by 0.865, and we would get 8.65 amps. Okay, and that would be the value of current that's flowing at the 2nd time constant. Okay, and so we would just follow through these values: 63.2, 86, 95, 98, and then 99%. And we can easily calculate how much current is present in the circuit at each time constant along that way. All right? Now the other one, this is for our rise of current. What we also want to know is what's the value of voltage? And voltage is not rising, but of course it is shrinking in this circuit. And what's amazing is that it shrinks by the same amount. I guess it's not really amazing because it's really just Ohm's law, isn't it? In a way, I guess. So all we got to do is have a 63.2% drop in voltage. So we would take our basically 63.2, write it up here, and we would sort of flip these percentages to indicate a drop from 100%. So at the first time constant, it would be 100 minus 63.2, and we'd be left with 36.8% of the voltage. Time constant 2 would be 100% minus 86.5%, and we would be left with 13.5% of the voltage. Time constant 3 would be the same process. We'd be left with 5% of the voltage. Time constant 4, as the voltage is dropping even further, we're going to be left with only 1.8%. And then at time constant 5, we're going to be left with about 7%. So you can see once again, by the time we get to even the 4th and definitely the 5th time constant, we've pretty much dropped to 0% of the voltage present from the source, okay? So we would do the same process, and we would take our 100 volts and multiply it by 0.368, and we would know that we would have 36.8 volts present at the very first time constant here. And we would just simply follow through with all of these values here to figure out the amount of voltage that's present in that entire process, okay? So basically what we have to take away from this video is that current is going to slowly rise to a steady state, and it's very simple to calculate that steady state. That's just simple Ohm's law here, 100 volts divided by 10 ohms, and we can go ahead and figure out what the max current is. We can figure out how long it will take, and that is our simple L over R formula, Henry's over our resistance, and we had 100 milliseconds or 0.1 seconds. It took 5 of those time constants to get to max, so it took a half a second to reach steady state. And then we use our 63.2, 86.5, 95, 98, and 99 percentage values in order to calculate the points of current, what value of current is available, or should I say going through the inductor at each time constant, all right? So I hope you enjoyed this video, and we'll see you in the next one.